Welcome to the RC Aero Design Build channel. My name is Tom, and I'm a radio control airplane hobbyist with an interest in scratch-built model airplanes. The purpose of this channel is to provide design and construction content that will hopefully be useful to anyone interested in designing and building their own model airplane. I'm a subscriber to Flow5, which is a next generation application created by the developer of XF-LR5. The user enters the geometry of an airplane as well as an airfoil, and then Flow5 can be used to analyze the performance and stability characteristics of the model. This is my first video for the channel, and it will be presented in two parts to demonstrate a new feature of Flow5, the ability to import and analyze STL mesh models exported from third-party CAD and design tools. In the background, you've been looking at the sample model STL file for a Cessna 210 with a modified wing. This model was created in OpenVSP Sketchpad by Brandon Litherland and then uploaded to VSP Hangar. VSP Hangar is a public database of models that users have created in OpenVSP and have chosen to share with other users. You can see that the STL model is a set of triangular panels that are representative of the underlying 3D model geometry. I've selected this model because there is also wind tunnel test data available that we can use when analyzing the STL model to compare to the Flow5 performance analyses. In this first video, I'll show you how to download the Cessna model, import it into OpenVSP, and then export the STL mesh representation of the model. In subsequent videos, I'll demonstrate how to import the STL file into Flow5, pre-process it, ready for analysis, and then to perform a performance analysis. So we'll start by downloading the OpenVSP application. OpenVSP is pretty easy to find. You just do search on Google, and there it is. Click on OpenVSP and it'll take you to their main page. So here's the download tab. Click on the download tab and they'll display downloads for Windows, Mac, and Ubuntu. So I'm running a Windows machine. This particular version, as you can see at the bottom left of the page, is Windows 64, and this one's 32. Just click the appropriate application version and download and unzip the file folder and simply run the vsp.exe file and you're ready to go. I'll now return to the OpenVSP homepage, and the next tab is the VSP Hangar, and this is a public database of projects that have been created by OpenVSP users so they could be shared with other users. There's about 335 models in here, and we're going to search for a Cessna. You can see here that it looks like there's about a dozen Cessnas. The one we're interested in is a Cessna 210 with a wing modification. So I'm going to click on that, and that brings up an information page for this particular model. So a few things of interest. This model was created and uploaded by Brandon Litherland. It was created in VSP version 2. We are currently using version 3.22, and it will not directly open this, so we're going to have to save this and then import it. I'll demonstrate that later. Other useful information. This particular model uses feet as its unit of measure. So when you look at OpenVSP, when we open this particular model, it's going to indicate that the span is 42. It doesn't anywhere indicate in OpenVSP whether that's in feet, meters, inches, millimeters. It's only through the information provided by the creator of the model that we know what the unit measure is. In this case, it's feet. Other items of interest are the quality of this model and the creator has indicated that the source material was good and that good 3-view drawings were used to create the model. Other things of interest is this link here. For this particular project, there was wind tunnel test data available, and if you go to this link, you'll be able to download the original report for the test data. So now I'm going to download the model. I'm going to save the file, and it opens up a directory on my machine for OpenVSP models, and in this case it's a demo. Here's the name of that file, and I'm going to save that. Okay, so now I'm going to open my version of VSP, and it's brought up OpenVSP 3.22. So first of all, I'd like to comment that it's not my intention to provide a how-to tutorial on how to use OpenVSP. That's beyond the scope of this video. The intent here is to provide you the minimum steps required to import a model from VSP Hanger and to do some minor edits and then be able to export it as an STL file so that you can import that into Flow 5. I will, however, include all sorts of links below the video that will provide you support documents and tutorials and videos that'll help you get started in the use of OpenVSP. So the first thing we're going to do is we're going to import the version 2 project file that we saved in our demo folder. If that file had been a version 3, I would have just opened it, but because it is version 2, we're going to import it. So this window opens up here that allows you to import a variety of different file format documents. The one we're looking for is right here, OpenVSP version 2. So we're going to click on that. I'm going to drill down to my demo folder where we had downloaded and saved the version 2 Cessna 210. So I'm going to select that, I'm going to accept it, I'm going to close this, and you can see this model is now imported into OpenVSP 3.22. The first thing you need to do, and I caution you, you need to do this, is you need to save this as a version 3 document before you start working with it. So it will automatically do that. We'll just rename it Cessna 210 mod version 3, and we'll accept that. Okay. If you fail to do that, there is a bit of a glitch in the import where the foils and some of the components may not display correctly. So the View tab allows you to manipulate the model inside the 3D space. So the first thing I'm going to do is fit it on the screen. And then we're going to go over, look at the Geom browser, and we're going to take a look at the vehicle. We can actually rename it Cessna. And we can see that it's made up of 5 components: a fuselage, a vertical stabilizer, horizontal stabilizer, the modified wing, and a hub. I'm going to select the hub because we really don't want the hub to be included in our STL mesh file for analysis. So we have 2 options. One is to hide this, but it would probably be safer if we just cut it and then we did a save. So next up is we're going to take a look at actual individual components. In particular, we're going to look at the modified wing. When you click on that, it highlights that component, and it brings up a window that displays all the parameters for that component. So right now we're looking at the plan view or plan form information for this wing. So it's displaying a span, a projected span, a chord, and an area and an aspect ratio. First thing I want to caution you, these dimensions are not the same references that you would use in your analyses in Flow 5. So we'll address that when we import it, but I'd caution you not to use it. For example, the chord is not a MAC, it's some kind of an average. The span is a true length span of all the wing panel components, which could include winglets, and also ignores any dehydro. So the one thing that I do want you to take note of is the span, however. Note that this is 42. It doesn't say whether it's feet or meters, as I'd indicated earlier when we imported it. The only reason we know it's feet is because the creator of this model told us that it was in feet. We're also going to use this dimension in approximating what size mesh we want to create. So I'm going to go back to the Cessna model, and then we're going to go over to the Analysis tab. This Analysis tab lists all the functions that we can use in OpenVSP. We're going to use two. One is the comp geom, and the other is the CFD mesh. Comp geom is a function that's going to check our mesh for us, and we don't really want to output any files. We just want to do an execution here. So I deselected these two output files here. We'll do an execution, and we're interested in the bottom line. If we had a mesh that was not watertight, it would indicate that here, and we would have to go back into the Geom browser and look at each of these components and determine what the problem was and fix that. In this case, it just provides us a warning that we have two open meshes, but they've been merged. That includes the horizontal stabilizer and the modified wing. So this model appears to be ready to generate the STL mesh. We're going to get out of that, and when we go back to the GM browser that's listing all the components, two things are apparent. First of all, it's created a new component, which is the mesh geom, which is the results of that analysis. We don't really need that, so we're going to cut that. And the other thing is that none of the components are showing anymore, and that's indicated in these component names. So in order for OpenVSP to do an analysis, it needs to have a component, and it only analyzes the components that are showing. So we want them all to show. We're going to select all, and then we're going to click show, and now we have a complete airplane that we want to generate an STL file for. So now we're ready to go back into the Analysis tab. We're going to select CFD mesh function, and this window is everything you need from here on in order to generate a good STL mesh and export it for use in analysis in Flow 5. The first tab I want to look at is Output. This indicates the name of the file or files and the location where this STL file will be saved. So there are over a dozen different file types here. The only one we're interested in is the STL. So what we're going to do is deselect all these others so we don't have a pile of files saved. And the other thing is we should check to make sure that we know where this file is going, and this STL file is going to go back into my demo model. So we'll go back to global, and this section here actually defines the size of the triangles in the mesh. And these values are default values that normally populated when you open this for the first time. So I'm going to include a link below this video which describes what all these terms refer to. But the bottom line is, the most important one is the maximum edge length of the basic triangle. So in this case, we know that we have a wingspan of 42, and we know that it's 42 feet. The maximum length of an edge of a triangle is 0.5 feet. So one of the things that we want to do is try to generate a mesh density of less than 15,000 triangles. And that's because more than 15,000 triangles, when you go to analyze it in Flow 5, is not going to add a lot in the precision of the analysis, and also it's going to use up a lot of memory in your computer, and the process will be quite slow. Typically we're looking at a triangle mesh density between 5,000 and 15,000 triangles. So just a really crude rule of thumb, I've found that if you take the span of the wing, which in this case is 42 feet, and use a value of 4%, in this case that would be 1.68, let's call it 1.7 feet. We'll enter that here, and the minimum length is usually 20% of that. So we're going to call that 0.34, and this maximum gap is about 1% of the maximum edge length, so we're going to call that 0.17. And the number of segments in a circle, for example, if you looked at a cross-section of the leading edge of the wing and drew a circle that represented the curvature, that the resolution would be, if you took that circle and created 16 segments, that would be the best resolution that we would get on this. I'm going to change this to 22, and this is the growth ratio, which means if you had a triangle, for example, that had a length of 1, the adjacent triangle, the maximum it could be would be 1.3, and the next one would be 30% greater than that, and so you have a sort of a controlled growth in the size of the mesh. The other thing we're going to tag along is we're going to toggle that we want a rigorous 3D growth limiting, and that's basically all we need. So we should be able to run a mesh right now, and this may take a bit of time, so I may speed up this. Okay, so we have a total number of triangles of 7,306, which is falls within the range we're looking for, and it confirms that it's watertight. So we could shut it down right now and then import that into Flow 5, but first I think we'll take a look at what that mesh looks like. So if I move this over and I look at the underlying wing, this is a pretty good representation of what that mesh looks like. One thing you notice that the density of the triangles on the leading edge of the horizontal stabilizer are quite good, but in the trailing edge the density isn't very good at all. We know that the best accuracy for doing analysis is where we have a good density on the trailing edge, and the higher the density, the better. If we look at the vertical stabilizer, we'll look at the left here, and we take a look at this, actually the density is very poor. So we'd like to make some changes to the horizontal stabilizer trailing edge and the vertical stabilizer trailing edge to improve that density. Let's just go back to looking at the wing, and the density is very good, so we won't need to do anything with that. So I'm going to fit this back on the screen. Well, I'll close this first and then select all, show. I'm going to fit it on the screen and do a top view. So I'm going to go back into the CFD mesh. You can see that the values that I typed in before have been retained, but I'm now going to show you a method for improving the density on the horizontal stabilizer. So we do that by looking at these sources. So we're going to select the horizontal stabilizer, and basically what we want to do is draw a line along here which represents where we want the better density. So we're going to select a line, and then we're going to add that source. So you can see these circles here that are indicating the area of influence where we're going to increase the density. First thing we want to do is we want to reduce this here to 0.5, and we're going to reduce this area to 0.5 as well. And then we're going to try to get this to turn into a straight line. So okay, so that should be adequate for the horizontal trailing edge. So that's going to basically, the influence of this area right here on this stabilizer is going to have an increased density. So let's look at the left side, and we want to increase the density on the vertical stabilizer. So we're going to pick the vertical stabilizer. We want to draw a line, and we want to add that in. And we want to reduce the radius of these as well. So we're going to change that to 0.5 and that to 0.5. And that's going from this point to this point, and so that should be sufficient. So now with those changes, look, keep in mind that last time we had a density of 7,300 triangles. If we run it this time, it's probably going to take a little longer, but it's also going to give improved density at those trailing edges, and it's also going to increase the total triangle count for this analysis. So we've completed that run. Let's take a look at the density on the trailing edge. Hard to see here, but the density is much higher on this trailing edge. Let's look at the top and fit this on the screen. Anyway, you can see the improved density here. Subsequent to recording this video, I realized that there was one main source control parameter that we hadn't addressed, and that is the length. We talked about the radius, which this dimension here, the radius, defines the area of influence on the rear trailing edge of the fin. And that's the dimension basically from here to here. But just as important is the length, and that length is actually the length of each triangle on the trailing edge. So in the previous analysis that I showed, I believe we used a trailing edge of 0.1, and we're going to change this to 0.4, and we're going to run this mesh again and take a look at how that changes the density of the triangles on this trailing edge. So I'll do a quick run here. Okay, so now if you look at this trailing edge, these triangles, the density in the length of the trailing edge and in the area of influence that we defined with the radius is probably a little bit more reasonable than the first time I did this. So it's important when you're applying these controls on trailing edges that not only do you have sufficient triangles in order to do a good analysis, but there's no need to have too many because it's going to slow down the process and not really contribute significantly to the accuracy of the analysis. As far as I'm concerned, this mesh is good to go. So what we're going to do is we're going to end it here, and then we'll import this mesh into Flow 5 and have a look. If there's any issues, we'll come back into this and make some changes. See you in the next video.